my presentation is hydrologic predictions or in forecasting, more precisely statistical data mining used in hydrologic forecasting and prediction. And the topic requires a few definitions, so I'm going to start with the definitions. For most of us, forecasting and prediction are one thing, but for hydrologists, it's different. And it's even recognized by the Wikipedia site. For hydrologists, the forecasting is estimation of some future conditions for specific future time, like day ahead, 2 days ahead, month ahead. For a prediction, it does not have a reference to a specific future time. So predictions could be 100 year drought, 50-year flood, or some heavy precipitation with certain return period. We know how big they are, how often they happen, but we don't know exactly when these events will happen. Now we collect a lot of environmental data, and the amount of data we have has been growing exponentially. So now we have a lot of data, much more data than we had 10, 20 years ago, due to cheap computer power, due to the monitoring technologies. And what do we do with the data? In order to utilize the data, we had to develop technology for that, and the technology is data mining. Data mining is an extraction of hidden predictive information from large amounts of data. We have mountains of data. We need to make sense out of it. There are many. That's also called knowledge discovery. There are many technologies that belong to data mining, starting from the statistical analysis, from the traditional statistics, regression tree, neural networks, genetic algorithms, genetic programming, fuzzy logic, and many, many, many others. They all belong to a large group of artificial intelligence. Now, neural networks are inspired by the function of human brain. They're nothing but multiple input, multiple output regression equations that change with time and reproduce the outputs based on the known input-output pairs. They're trained or calibrated similar to other traditional calibration methods, other than the only different aspect is they have a lot of randomness, and that's why they are good in searching of the optimum solutions. Genetic algorithms are inspired by the natural evolution, and they can be used to estimate the optimum parameters of any model. But they also are used to estimate the best models for certain problem. And they're also calibrated similarly, like artificial neural networks, through some kind of random choice and fast search mechanisms. I'm going to show you three examples. The first one will be about forecasting, and the second two will be prediction, given the above definitions. We used a state water survey. Our team used artificial neural networks to predict nitrogen concentration in the Sangamon River. And if you look at the top chart, you will see on the left side, the model and the observed are not as close as on the right side, meaning that with time, the model learns about the relationships more and more and more, and that's why it's intelligent. That's why it's called part of the artificial intelligence. It does learn the complexity of the problem, and does learn the parameters in the types of relationships. The genetic programming approach that we used gave us 11 equations, and we studied them, compared them statistically, and out of these 11 equations, we found 2 of them that have the best statistical parameters. The genetic programming, therefore, finds the best predictive relationships for you. It can be intuitive, it can be counterintuitive, but most of the time it's very useful for us. Second example is flood frequency analysis performed on the Pecatonica River in the northern Illinois. It was a pretty challenging problem, so we had to show a high degree of creativity. And the last example that I'm showing you is the future climate change under future climate scenarios and its effect on future precipitation frequency. These are all the examples I had today. I'd like to finish this presentation with the final recommendation: mind your own business. Thank you.